Hi, good afternoon, everybody. Welcome to the webinar by the Solar Labs. This is our second webinar in the series where every Saturday at 4 p.m. we gather here to learn more about solar design. And we also showcase the software called the Solar Labs. Uh, in this edition of the webinar, we'll be talking about energy simulation reports and how we can create them using the Solar Labs software. So I would really request everybody to have their mics on mute and their cameras shut off. And you can pin my screen as well on your browser so that we do not switch between screens. So just wait. How we are structuring today's talk is that we'll be talking about this company, the Solar Labs. Then we'll come to the topic about the need for performance simulation or energy simulation. Uh, in that, we'll be covering a lot of, discussing of factors about what affect energy output of solar PV plants. Uh, the next step that we'll be talking about is the energy loss diagram that is created by the TSL software. So this will be a mix of what we have the theory about in general about energy simulation, as well as how TSL software tackles all of this theory into practical applications. We'll be talking about, in theory, what are the different stages of energy simulation, what are captured by TSL, and the product roadmap. So I like to talk here about a lot of things which the software is already created and how what parts of the software can really help you in creating better energy simulation reports. We'll be showcasing how the TSL design reports align with PVSys reports. And then we'll be talking about very interesting 4 cases about how using the Solar Lab software, you can create better designs and how we capture three major factors that are required in energy simulation, which is how energy simulation depends on. That is the lat long of the project, the weather data, and the mechanical design uh, of the plant. So we'll be talking about 4 different cases about what insights we get about energy simulation using the software. And then if time permits, we'll go into a demo and then a question and answer round. Uh, so quickly, talking about our company, the Solar Labs. So we are a software company based out of Delhi in India. And since 2017, we have been in the market and selling the software since 2019. So we'll be talking about what is our software, some of the designs that are created using the software. So it's all about solar design of rooftop plants, how we suggest that people can use our software for remote sales and operations, and some of the key features that are there in the software. So TSL was founded by IIT alumni from 2017 to accelerate the adoption of rooftop solar in the world. So how do we intend to do that? We want to provide the best improvement in workflow for solar system design practices, where our customers can do two important things. They can create good designs of solar plants and also use our software to create sales proposals so that they can they can convert more customers. So far our software is used for estimating 100 megawatt of capacity in India. Let's have a quick overview of the solar industry. So the solar industry in India specifically rose from 161 megawatt in 2010 to 37.6 gigawatt in 2020. Out of this, rooftop solar makes up almost 4.2 gigawatt in Q1 of 2020, whereas there is a long way to go, and we hope the Solar Lab software can contribute to India's journey in reaching those lofty targets set by Government of India. Moreover, solar industry is one of those industries in the world right now where there are massive investment opportunities and options for job creation. So we hope solar industry is a driver for growth in especially this post-COVID era where India can become a world leader. So let's talk about the solar labs. Exactly what are we offering? So using a software, we are going to enable our customers grow their sales. How can we grow your sales is because we believe data-rich proposals can tackle your customers' pain points. You can use these data-rich proposals and an easy-to-use software to convert more clients. Then the second thing that we could do using that our customers build using a software is create optimized designs which help creating better performance PV layouts. So there's always a question, right? What is the best design for that client? Based on a lot of parameters on site and especially within your team, from design engineers or sales engineers, we want to give you a software that simplifies every step of solar design and help you create the best designs possible. Overall, using a single software for all your needs, we will help you reduce costs. If you're really interested in creating the best designs possible and converting more clients, instead of using multiple softwares, we provide you a single software that can automate your work and help you win more customers while reducing costs. So a software can be used to create a lot of different residential designs. You can see that there are certain RCC roofs, there are certain shed roofs, and also you can create roofs for residential customers. As you can see in this design, this is the 9 kilowatt system. You can create complicated roofs, roofs like which are dome shaped. You can create roofs which are having multiple tables of different sizes. This is a 100 kilowatt system. You can also create roofs with a 200, this is a larger roof of 240 kilowatts. So the intention here is that all your 3D modeling and different types of module layouts can be created in software, which is not only a preliminary estimate, but it can also be installed on site. So isn't that what we all want? You want to have a design which is applicable in real life, right? So a software is able to provide you all of that in a very easy way. So one of our customers from Amplus Solar and one of our customers from Vari Energies Limited, they point out the similar thing. It's a very easy to use software where in just 2 hours, okay, you can learn the software and create designs in just 20 minutes. We have so far got 110 customers from India, and we hope to be contributing more to the nation's economy and to our partners. There's one unique thing that we want to be able to provide here. Right now, the industry is quite fragmented. I mean, the people in your team are using multiple softwares. The marketing team might or might not be using any software. Technical team is using different softwares, and the execution team is again at the mercy of the design team. So we intend to bring all of you at a single platform where you can convert more customers using sales proposals. You can create design reports which are very accurate and implementable on the ground. You can create 3D models and CAD layouts. Apart from all of the design work, we can create energy simulation reports. Now, these reports are directly created by the software, and we do very well with respect to mechanical design and engineering. But if you would require energy report, which is accepted by other financial institutions, you can export files from a software and then import into PVsyst. So again, it's a single software that can unify your entire process. So we have a lot of partners across India for different purposes. So let's not go into it. We also provide consultancy, where on a side-by-side basis, we can provide you detailed design services. We can do drone-based services so that we can help you reduce your costs, especially in the time of Corona, where traveling is seen as a problem. You can outsource that work to us so that we can collect data via drones and provide you the accurate 3D dimensions. So we also provide training for rooftop solar using our software and in general where it can be for sales or for detailed design. We have recently started focusing on providing an enterprise level software solution where if you're having multiple channel partners across India, all over through the world, you can get your entire team onto a single software so that you can manage your operations better and scale your company to greater heights. So this is one of the interesting things that the Solar Labs has been working on. It's called large scale analysis. This is the last thing about a company, and then we'll quickly move on to the energy simulation and what we have in store for you in this webinar. So this large scale analysis is a product which the Solar Labs is developing, where we will be able to map out large areas using drones and then model those designs, the 3D models in our software, and then accurately estimate system capacity. Now imagine if we can determine based on one study in Mumbai where 1.5 gigawatt of solar can be installed in that city. So we can help governments and private companies be able to create solar designs without even visiting their sites. So this is something that we have been working on. And now let's quickly move to our energy simulation webinar today. So we have covered the introduction to Solar Labs. I hope you get what our software is about. And then now let's focus on the need for performance simulation. Right. So there are three major measurements that require that in any solar plant we have to measure. One of them is called annual production. The second one is performance ratio, and then specific generation. Each of these numbers are very important to predict the quality of a plant or how much energy a plant is generating. So since this solar plant system lasts for 25 years, we need to have at least a basic experience or understanding as to what your design is going to be capable of. Now, as we all know, in designing a solar plant, there are X number of factors involved. But when you're doing performance simulation, there is one trade-off that we have to always talk about. Either your design is looking for higher lifetime financial savings, or are you looking for lower payback periods? Because there's a trade-off of quality and there is a trade-off for higher expenditure, but overall larger savings. So we need to have a performance simulation system, a process in our company or in our design process where we can provide best value to our customers and help them take a better decision. So let's take a quick overview of the factors that affect energy output. I'm sure all of you might be knowing some of these or a few of these factors that affect energy output. So let's quickly understand as how these factors can affect your plant output. So we are talking about the plant location, we're talking about weather data, we're talking about how the earth moves around the sun because of the declination angle and the distance from the earth to the sun. There's a lot of variations that happen, which is again dependent on latitude and longitude. So these are not individual factors that you can create energy decisions based on your thumb rules. You need to understand, or we need to have a tool that can connect all of these factors and help us take intelligent decisions in a somewhat automated way. That's where our software is able to automate a lot of features, a lot of time consuming data process steps. So of course, we know that environmental conditions are different. I'm sorry, can somebody's mic is on unmuted. Can you please mute your mic? Yeah, thank you. So yeah, like I said, now there's one more important factor that even if we design the best solar plant that we can, there's always going to be a problem if we do not take proper maintenance or if we don't maintain our plant well, and that affects our soiling and the downtime. Just a second, let me see if we have to mute somebody. Okay. Okay, I'm back. Yeah. So that's an overview of factors that affect energy output. So let's now talk about how these factors are taken into account by the TSL software. So this figure that you see here, it shows that the different losses that are needed in an energy simulation is covered by the Solar Labs. We have divided these losses into 4 different stages. So as you can see here, these values, by the way, are just for indicative purposes. This is one of the outputs that is created using the software. So we have 4 stages, like I said, and we'll go into detail about what is the importance of these stages and how these stages, play a role in determining the final energy outputs. So the first 2 stages are around incident energy on the panel. So when we talk about incident energy, we have to first take a step back and understand how the solar plant works. So we know that the solar plant works on photoelectric effect, and the photoelectric effect works on the amount of sun radiation that falls on the panel. So this first part, where we talk about the radiation from the sun that is captured by the panel, is considered in stages 1 and 2. So our software, through a lot of algorithms and weather files that are available from the industry, we are able to capture this data where we are able to determine what is the exact amount of energy that falls at the panel. Now, this is something which is related to a lot of physics and weather and location. So these factors are very specific to where the plant is, placed. So this is weather and location related factors, stage 1 and 2. Then in stage 3, what we have is after the energy is incident on the panel, the photoelectric effect comes into picture and converts the incident energy into usable electrical energy in DC format. DC means direct current. So here we are talking about the electricity that is exported from the panel until it is reaching the inverter. So there are multiple steps involved, and this part of the solar panel system is related more to electrical design and engineering. So electrical design and engineering is a separate stage, which is in stage 3. And here, right now, a software is able to do it on a manual, like you can take into details in a manual way, whereas we calculate the environmental losses about the panel automatically. Then we talk about the last stage, which is stage 4. Here we will talk, we see that there is a loss happening at the inverter efficiency level and then at the wires of the AC cables. So from, like I say, from step 1 to the last step, there are a lot of losses that can happen in the solar design. And all of these factors will impact your final energy outputs. In this webinar, we are going to be focusing on stage 1 and stage 2 and up to the first part of stage 3. The rest of the parts which are related to electrical design will be taken up in a separate topic as a separate webinar, right? So let's understand a bit more about what I just spoke with respect to what are the different stages of energy simulation. So there are two stages. The first two stages, stage 1 and stage 2, are related to incident energy. The factors are weather files, mechanical design, and the panel cover, which is the glass that is on the panel. So we get the data from we get the weather file data from different sources, which gives us the horizontal global irradiation, and this has a very high impact on the total energy of your system, right? So if we have only accurate data, relevant data from the past few years, we will be able to determine what the system is going to be generating over the next 25 years. Like if we have older data, it's not going to be that useful because a lot of patterns change in weather these days. Then we have the mechanical design part, which is very important here. Based on the tilt and azimuth, the incident irradiation on PV plane is calculated using a TSL algorithm. It is again having a medium impact because if you're not creating a good design, you will end up creating a very higher payback period for your customers. Then we also take into account the shading losses through our own algorithm, and it's very high impact because if you're creating a amazingly designed solar plant and you're not taking into account the shading losses that can happen, how will your system even work? So all of these factors are taken into account until the incident energy stage. And then there are two smaller factors which are not really under our control. These are factors which are under panel manufacturers. So that is about incident energy 1 and incident energy 2. And then we have already spoken about DC energy and AC energy. So our software has the thousands, or I should say 10,000 panels inside our software with their dimensions and their specification sheets. So a TSL algorithm converts, takes care of both the things, the weather data, the energy falling on the panels, and the panel specifications to create what is the final DC energy output. And this is a very high impact. So there are a lot of other electrical design parameters which have some low to medium impact on the final numbers. And these features are under development, and we will be out by most of these features in the month of October. So let's come to the interesting part where everybody in the industry who uses PVsyst understands the loss diagram of PVsyst. When we place the loss diagram created by TSL, you can see that every important factor which is researched in how to create a solar design system and how to create the energy simulations is also captured by TSL. We take care of all the mechanical factors and the DC energy output, but we are still working on some of the electrical design parameters, right? So that is why the solar labs can help you create amazing, mechanical layouts, which of course you cannot do in PVSys. So we are trying to link the two softwares so that you can give the best value to your customers. Now let's come to the interesting part. We'll talk about the cases that go into more detail about the different steps in mechanical design, weather data, and latitude and the location of the project, how these affect the energy simulation. So as everybody in the industry, right, has seen this graph. This graph talks about the global horizontal irradiation in India. So India is a very lucky country to receive a lot of energy from the sun throughout the year. So we actually can have some kind of reliability with respect to solar plants. So what is global horizontal irradiation? This is the total amount of shortwave radiation received from above by a surface horizontal to the ground. So this is the step one that I'm talking about, that we only get the amount of radiation which is horizontal to the ground, and we need to then convert it into a usable format for your PV design. So this data can be captured from different sources. It is also measured using a tool called pyranometer. This pyranometer tool is fixed at different locations across India. There are multiple companies that have their weather monitoring stations, and they capture this data from a very long time. This is a long-term average. This graph is a long-term average graph of 1999 to 2018. So how do we denote this energy, right? Now, we're talking about energy that is being received at the surface of the Earth. So it is denoted by kilowatt hour per meter square. So we have this data in the form of per meter square, like in the form of per unit area, basically. So what is the solution? Like, how do we take this into account into our software? So different locations have varying values as per Earth's weather. So historical data is provided by a few agencies. So we utilize all of these weather files from Meteonorm, from Solar GIS. You can upload a lot of your own weather files. So if you want to create your more detailed energy output reports. So what is the impact? So even if you create a system with the same design parameters in different parts of India, they will have different energy outputs. So if you have experience of creating good systems in Pune, you might not know how to create a better system in the city of Jaipur or in Kolkata or in Delhi for that matter. So instead of relying on thumb rules, the software can help you tackle all of these issues with some basic information. So what we have done is that we have taken a case of 6 cities in India. We have taken cities across north where we have we have very different weather parameters and the latitude is different. We have come down to south until Bangalore, about to see how this varies. We also have gone from east to west, taking into account Kolkata and Ahmedabad in our experiments with the software and to learn how these factors affect energy outputs. So these annual GHI values, which are taken into the software for these 6 locations, as per our software, have been presented to you. So we have, these are in ascending order. So annual GHI values, this is the total energy per unit area from Mandi, which has a very high latitude, is in the hills of Himachal Pradesh, versus Bangalore, which and some parts of Gujarat and Rajasthan, where we have very high annual GHI values, and especially certain parts of Karnataka as well. That's why Bangalore is at a very high annual GHI. So we have got Mandi, Kolkata, Noida, Leh, Ahmedabad, and Bangalore. So these are the annual GHI values from our software. And let's now correlate these values to the annual production that we see using our software for these different locations. What we have here is a design that I created for a 30 kilowatt system, precisely 31.08 kilowatt system. I used a module of 370 watt peak and an inverter of 30 kilowatt. I created a design which is true south and azimuth and at a tilt angle of 15 degrees. So this is the parameter which is same across all the different places. We have other parameters also, which are manually set in the software, which is again similar for all the different locations and all the different projects. And we are just trying to capture here the impact of the variation in weather and how that impacts, total energy outputs. So you can see that Kolkata is one of the lowest energy outputs in India, and we'll see even further that, like we see in the market, that West Bengal and East India has very little solar, very little solar market penetration. That is because the payback periods are higher over there compared to Gujarat, Rajasthan, and Bangalore. Delhi is still decent. The central India area is very decent, but the entire Gangetic plain, according to this graph, we have lower energy irradiation. So you can see the light yellow area from Kolkata to New Delhi along the Ganga River, we get lower energy irradiation throughout the year. Whereas Rajasthan, in Leh Ladakh in the north, and in Bangalore, which is the darkest of the red regions of India, we get a lot of output, like higher output energy. So according to my designs, Leh Ladakh is the highest energy output. And it's quite interesting what we have observed about the monthly output of Leh Ladakh. Just stay until the end so that we can see how our energy annual outputs depend on the monthly output, right? So in a software, you can upload your own data. So if you do not like to use Meteornom files, you can upload your own data of NREL, 3-tier, or Solar GIS. If there are any questions so far, please put them up on the chat icon using the meeting chat. Somebody from my team can then ask these questions to me. I'll be happy to take them if there are any questions right now. Okay, so now let's move on to the next step. So like.
This is Bhaskaran.
Yes.
Yeah, I means we have one. Yeah, Bhaskaran from IRradiance
Mr.
company.
Bhaskaran, please, please put in your questions in the meeting chat, and then somebody from my team will take up these questions. My team is also in this meeting.
Thank you.
Thank you, Mr. Bhaskaran. So yeah, now we'll come to the next step, which is step 2. Tilt and azimuth is linked with energy on PV plane, right? We saw the different stages, and we're still on stage 1, where we'll be now talking about the tilt angle. What is tilt angle? Of course, everybody knows I hope in our group today, everybody knows what is tilt angle. It is the angle of inclination of the modules with respect to ground. Okay, so the angle beta here you see is the tilt angle, and 0, when we take this value as 0, this becomes flat, like flat to the ground, and that is where GHI is measured. So you see this yellow line hitting the graph, right? This is the angle of incidence of the energy from the sun, and we try to calculate what is the energy perpendicular to the module. That is what is called step 2, because when we are talking about photoelectric effect, we try to understand what is the actual energy incident and how many electrons can then be freed from the panel. So let's also understand what is azimuth, just to clear our concepts and what we are using in the case studies. So azimuth is the orientation angle of the modules, right? It is the orientation angle of the modules with respect to north-south in India, and we take into account true north as 0 degrees to true south as 180 degrees. So you can see that based on its direction, in India mostly azimuth angle can vary from from anywhere from 145 degrees from southeast to somewhere around 220, 230 degrees to southwest. Any of those designs in India do work really well, right? And tilt angle varies from anywhere from 5 degrees to 25 degrees based on the location and the design that we require. So how can we automate this parameter for better design? Because we understand that this is quite complicated. At what angle does the sun ray fall on the panel, right? Now, we cannot have some kind of an Excel file and we just try to do it. We need a proper algorithm that takes into account this. factor, and that tool inside a software is called solar axis. Okay, so now this solar axis is, what is solar axis? So solar axis is actually a percentage, and it shows us the deviation from maximum incident energy at that location. So for every location, there is the software automatically calculates like what is the best parameters for design here and what can be the maximum energy. And then based on what we design, the software gives us the deviation that this design is just say 95% of your best design. So this number, by the way, solar axis also takes into account this if impact of shading. So if you want to increase solar axis and we want to reduce shading, the system capacity will reduce, our annual output will reduce, but our shading loss also will reduce. So we try to take a balance right now. What is the best design as per our financial analysis? I'll quickly jump into a small demo of the software so that it's easier to understand what I'm talking about with respect to solar axis. So I'll be opening up one of my designs. So this is my software. It's an online software which can even run on mobile internet. So right now I'm doing this entire webinar on my mobile internet, and I hope it just works. It works as smooth as butter. Like you don't need a lot of data bandwidth for this. So it's a software which can help you create 3D designs, shading analysis, energy simulation reports, and even financial analysis. So I'll just quickly show you what I mean by the solar axis. So we'll just create quickly a design here. I'm creating a small building which is based out of Noida. There's something. So I'll be creating a small building here. This is, yeah, I'm giving it a height of 10 meters, and I'll give it a parapet height of 1 meter. Okay. So this is a quick building that I've started creating, and I'll create some of the obstacles, just some of the obstacles to show you how shading is captured in a software using solar axis. So this obstacle is 3 meters tall. You can see that when I switch on the sun simulation tool for different dates of the year, we can see the shadow pattern from where the shadows can be on the roof using this sun simulation tool. So we'll use a method called fill face here to place the panels quickly, the maximum number of panels that are possible on this roof. And by the way, you automatically see that the panels have been kept at a certain distance from the edge because of the setback values that we have already set into the software. So we'll quickly, change some of the parameters, give it a height of just 0.5 meters tall, and create this module layout. What I'll be doing next is, once I've created this module layout here, by the way, we have taken into account the inter-row spacing as well. And if you wanted to create more detailed layouts, you can literally just copy modules. You can drag them around, paste them as you will, create accurate layouts. But now we're just focusing on solar axis. I'll go to my solar axis tool, click on show. So here we are trying to capture the amount of energy that can be exited, output from the panels based on the design of tilt, azimuth, and shading, right? So you see that these panels on the rightmost side, which might be in shadow, are having a solar axis value of just 95.3%, whereas these dark green color panels have a solar axis value of 98.1%. You can notice the solar axis value on the right hand side. So this is what I intend to show you, where if I change the tilt angle, suppose I change the tilt angle to 5 degrees, I'll increase the row spacing to 1 meters. Let's just place the panels very far apart. There should be no inter-row spacing. And I'll click on the sub array here and click on refresh for solar axis. So what happens here, when I reduce the tilt angle to just 5, you will see that the the solar axis has gone down further to 92.7, and these tables are at like 86. These tables are at just 86 solar axis value. So I want to create a better design. So I'll go to 22 tilt angle. I'll give it an auto row spacing mode, increase the height to say 1 meter, and click on update. And that's how, using a software, you can create initial layouts very quickly and create optimized layouts as well. So I'll just remove the panels with the lower solar axis value. And here, as you can see, I've created a design with 98.6 degree solar axis and a total size of 156 kilowatt. So basically, this is a small demo of how solar axis can tackle tilt angles and as well as azimuth angles. So basically, I can also change the azimuth here and show you the same impact on solar axis. So I'll quickly move back to my presentation here. So you have seen how tilt angle, azimuth angle, and shading is captured by a software in an automatic manner. And let's talk about one of the cases. So this is a Noida case, and you can see we are talking about solar axis values for azimuth of 180 degrees and an azimuth value of 150 degrees. So of course, for the same tilt angle, the azimuth with 180 degrees has a higher value of solar axis. So as you can see, the worst value here is 150 degrees and 7 degrees tilt, which is 93.5. And the best value is tilt angle of 22 degrees at azimuth 180, which is 99.2. Now, this translates into a very important number called percent increase on PV plane. So this is what we have been talking about so far. What is the incident energy on the module? And it is captured as 10.52% increase. And this is for the case of Noida, whereas it's only 4% increase when we are talking about 150 azimuth, right? So we want to create better systems, and the software can tell you how do you create a better design. When we compare this to now a different location in Bangalore, right? What did I observe? So here you can, and I'm sure you must have seen this in your experience now, because Bangalore is at a lower latitude. The When we make changes with respect to azimuth and tilt, we don't see a greater difference in solar axis. And that is what you can check this out even for Monday. You can pick this up for Coimbatore. You can pick this up for Leh Ladakh. As now, why does this happen? It's because of how the sun, how the earth, how the earth moves around the sun. Now, let's talk about one of our curious cases here. Um, Imagine you're creating a reverse tilt module layout, right? Reverse tilt module layout on a north facing roof. uh, you want to create, a better energy output. So if you're creating a north facing roof with tilt facing south and azimuth facing south, your solar axis value is 94%. Whereas if you create a flush mount system, okay, if you're creating a flush mount system, your tilt angle is just 10 degrees and your azimuth is facing somewhere in the north hand side and your solar axis is just 84%, right? So a software can quickly give you an example of how to create a better layout. But here there's one important factor. We are designing for maximum specific generation when we look at solar axis. Whereas when we look at maximum total energy, it will be higher with the flush mount system, as it is a 102 kilowatt system. If time permits, I'll show you both of these designs on a software and how we create the energy simulation reports. Let's quickly look at a factor called irradiance after reflection. Again, this part of the energy simulation is captured using an algorithm created by ASHRAE, which is the American Society for Heating, Refrigeration, and Air Conditioning Engineers. These are losses which are caused due to simple physics laws, that any light hitting glass or any interface between glass and changing medium, it will be reflected or absorbed. So it is an unavoidable loss that happens in any solar panel system. But it creates an impact in a way that it is dependent on the nature of material used on solar panels. So if you have a panel which has an anti-reflective coating, please go ahead and purchase that for your good systems, because anti-reflective coating on the panels will help you reduce these losses. And if you want to create a more expensive systems, you can use the solar trackers so that you can optimize incident energy, right? So the irradiance after reflection depends totally on the angle the sun ray makes with respect to the panel. So if it is hitting perpendicularly all the time, this value can be reduced to almost zero. I just have a couple of little bit of water. So if there are any questions, by the way, I can take them up.
Yes, so Rishi, I think due to some problem, the chat box is not coming up. So we'll one by one, we'll take the questions verbally. So if you have any questions, you can turn on your mic and ask your questions.
Okay, so let's just take two questions now, and then we can move forward.
So yeah, Mr. Amit, you can go ahead with your question. So as Mr. Amit has initiated, you can raise your hands and then you can proceed with the questions.
Is there some problem here?
Yeah, Mr. Amit, I will request you to turn on your mic and ask your question.
Okay, it seems like let's just do the webinar in one go and keep the questions for the end. I think that should be a better way to go ahead, I think. Right. So yeah, we have just 15 minutes left, and we can quickly tackle all the issues that we're talking about. Um, just a second. Yeah. So now let's talk about one of the important factors that we take into account. Now this is called step 6 and 7 based on the figure that I showed you. Don't worry, I'll be sharing you this document and the meeting recording so that you can go back to it. I'll also be sharing one of the documents which is already present on our website regarding performance simulation in TSL. So you'll understand what is step 6 and step 7. So this is in stage 3 where we try to calculate based on what is the energy incident on the module, and it gets converted into DC energy. So this is dependent on panel specification sheet. Now every module manufacturer has thousands of has a lot of SKUs where for they use different cells, they use different technologies, they use maybe half cell technology, cut cell, half cut cells, they use multiple bus bars, diodes. So the quality of the cells, which is then determines the efficiency of the module, all of these factors are preloaded into the software. So we know the maximum rated power, the operating voltage and current for the module. So the graph that shows on the right hand side is about how at different irradiance levels from 250 watt per meter square to 1000 watt per meter square, we get different energy outputs. So basically, what is the operating principle of the panel? It's the photoelectric effect. And that is how these graphs are made and they depend on. So these graphs are, by the way, whichever panel specification sheets are available, which is goes into step 6, is at STC, that is standard test conditions. So the power output is dependent on the IV curve. And this IV curve, since it varies for different temperatures and different irradiances, at standard test conditions, the module, rated power and other qualities are rated, are given to us. So if we have to take into account, I'm sorry, yeah, if you have to take into account the impact of environmental factors, so we have multiple models running in the software that can do this from temperature 0 degrees or to a temperature 50 degrees. We can see what is the impact on the energy output, and as everybody knows that when the when the ambient temperature is higher, our total energy is impacted adversely. So our total energy output of the modules reduces. So again, for these few sites, I have done the same experiment, with respect to all the 6 sites. I have arranged them in the order of increasing annual output. So here what we observe is that Kolkata is at the lowest and Leh is at the highest value. On the first column talks about the total incident energy with respect to GHI and what is the solar axis for that design. So you will observe here that the solar axis for Mandi and Leh at 15 degrees is low. So it is not a good design. We have to have a better tilt angle for that location. Then what we have that for Bangalore, 15-degree tilt was the best design. And we, of course, see that the final irradiance and the annual output is also high. But of course, that is also dependent on the incident energy. So overall, the column, which is environmental condition, this factor is in percentage values. And this amount of energy is reduced from the STC energy output. So our software takes into account this value and then you can get the annual output in megawatt hours. So for different locations and for different places based on the weather file, the environmental conditions factor is taken into account by the software. So now let's move on to the final step that we have here, which is monthly variation in output DC energy from panels. So like I said, we already, gave you a small hint about what this is and how. Now let's talk about what is sun path and how it depends, like what depends on it. So what we have here is that the sun in the sky moves in a very peculiar fashion, which is perceived from Earth, right? So this is called sun path, the motion of the sun in the sky. And we have to now understand why does the monthly average solar irradiation change. So this is a small diagram called iso shading diagram. It's a bit complicated to look at, but quite easy to understand. It's displayed by PVsyst, and we also take into account these factors when we calculate the output from the Solar Lab software. And here we are talking about three important factors that determine the monthly energy output. So we are now talking about what is the available sun hours for that location. So summers have higher intensity sunlight from 8 a.m. to 5 p.m. So our plant produces more electricity, whereas winters have lower intensity sunlight only from 10 a.m. to 3 p.m. And depends on other locations, but the window for energy generation is lower, and that is what is depicted by this graph. Here we have for different days of the year from 22nd June to 22nd December and back, how the sun moves and for how long is the sun actually visible to the panels, right? So this is something which is taken into account by the Solar Lab software, and we combine the different orthogonal factors, which is monthly weather data, available sun hours, and angle of incidence to create usable reports. Now, let's again understand the variation in the monthly energy output. So this graph gives us a brief understanding, that throughout the year from January to December, our energy production can vary a lot. Why? What I mean by a lot is that here the minimum energy is varying from 30,000 units per month to 42,000 units per month, right? So why does this happen? What is happening? So the second curve, which is in the blue color, is the average solar irradiation for that month, for that for the days in that month. So that is why we are able to then capture based on the angle of incidence and the weather data how the weather the variation happens. Now what is the impact of this? So in a lot of places we are trying to match the load, the captive load of the person who is using the solar plant with solar generation for the day and month. And the second part is that we have to take decisions regarding the best design parameters for that particular location. So in this graph, I'm showcasing you some interesting things about the case study that we have done, which is from Mandi to Bangalore. From it is the data for all the 6 cities put on a single graph. On the left hand side, we have the monthly production in kilowatt hour. Each and every city has got 12 different bars here, and every month is showcased in that way, and it's for different cities. So notice here two things. Every city, like Kolkata, Noida, Ahmedabad, and Bangalore, see a dip in the months of June, July, August. And of course, that is expected because that is the monsoon season in India. So we have a lot of cloud cover and a different pattern happening there. So we see a dip on almost every city. But that is not the case in Leh Ladakh, because Leh Ladakh being such north, there is no concept of monsoon season. And actually, the peak of energy generation coincides with the longest days of the year, which happen in the month of May, June, July. So that's the first thing that you notice, which our software is able to capture. Then the second thing that you notice is that of course, the software takes into account the temperature variations for those particular months, right? say for in Bangalore. Bangalore has a very unique weather profile. Bangalore weather is very cool, almost throughout the year. Of course, it's changed in the last few years, but in Bangalore, you can see we are seeing peak generation happening, in the non-summer months as well, and we see very low generation happening in the month of June, July, August. So these are a few insights that we are able to capture from the weather data and how monthly energy variation, output changes. So I think I do not have time for a demo, and because if there are any questions, I would love to take them. If the meeting chat is not working, please unmute yourself and uh, present your questions.